There we go. Oh. Okay, things are happening. How about that? Only 9 minutes late. I got shredded. It looks like I'm a rat up here with all this shredded junk, making a nest. Let's go ahead and start with the word of prayer. Dear Lord, I thank you for unexpected things. They keep life interesting, and honestly, even though they can be like a little bit in the moment, it's really nice to. I really enjoy looking back and having had things not go according to plan. Sometimes it makes me happy. But I just pray right now that even despite these crazy circumstances, that we can still get down to business and learn the things that you want us to learn about, some really incredible things that you do. And just also pray for all the students here right now. Just kind of like today with this class, some things in their lives might be going not exactly according to plan. I know that happened to people on their shoes. So I just pray that you're with them through those things. And even though those things might make school seem really kind of inconsequential, I just pray that you stay with us and help them persevere. Pray this in the name of your Son. Okay. Let's see here. We're going to talk about enzymes and metabolic control again. This is where we started out. We're going yesterday. Yesterday, Monday. Wait, today is Monday. On Friday. Okay, I don't know what day it is. And we're going to continue on with this. So we had been talking about different things that control the rate or enzyme kinetics. We've been talking about Line-Rupert and Michaelis-Menten kinetics. And now we're going to talk about other things that control the rates of enzymes. Particularly, we're going to talk about these things called enzyme inhibitors. Now, enzyme inhibitors fall into two really broad categories. The first one of these is we're on the irreversible inhibitors. Wow, I feel like I keep talking to you guys. Walk all the way around. Anyway, irreversible inhibitors, they bind covalently to enzymes. Wow, the freedom I have in here. So they bind covalently to enzymes, which means that this is irreversible, this is permanent. When you have something that binds covalently to your enzymes, it's not really. So it's okay, my wandering around is going to get me in trouble here. When you bind something covalently to your enzymes, you're not going to be able to pop it off all that easily. So this makes it so that this enzyme, for essentially forever and all time, is non-functional. It's dead. And to really get functional, I mean, you're going to have to recycle it. And that's, not how most things. This generally is not used by biological systems on purpose. There are inhibitors, like irreversible inhibitors that are, for instance, toxins and venoms and other things like this that biological systems will try to use on other organisms. But generally, this is not the kind of inhibitor that your biology wants to use on itself. It gets to be really metabolically expensive to completely break down an enzyme and create a new one in its place. But, yeah. No but, just that's that. And then we have this other broad category called the reversible inhibitors. Now, these have a couple subcategories inside themselves. And the first that we want to talk about is this thing called competitive inhibition. Now, competitive inhibition is interesting because the inhibitor in some way resembles the normal substrate. So what it does is it binds to the active site and actually competes with the active, or competes with the normal substrate for that active site. This binding, when it binds to the active site, just like the actual substrate, will bind non-covalently. This is going to be somehow through ionic bonds, maybe through hydrogen bonds, some other form of bonding is going to happen, which means that this is a permanent. This will pop off at some point. Now, the nice thing here is that raising the concentration of your substrate can overcome competitive inhibition. The reason reason for this is, imagine, okay, let's go back to our apples thing again, right? I'm picking up, someone liked that. Someone said yes. I'm glad that my analogy works well for people. Imagine I'm in this apple field again, and some prankster put in foam apples. And you know what? You cannot bite into a delicious foam apple. Have you ever tried that before? Yeah. Actually, I have done this when I was a little kid. You know how people put out fake apples on their tables sometimes because, hey, they don't feel bad and they have to switch them out, and then little kids can come by like, and it's not good. Okay, so the point being, okay, I'm in this apple field, I'm picking up my apples, and someone put these darn foam apples out there, right? It resembles the actual substrate. So if I'm going around and I'm picking up, like, imagine, let's say half of the apples are foam, and I can't tell the difference because I'm not very smart for whatever reason. Normally you can tell, but you know me, I'm kind of slow. I'm not able to tell the difference. So I keep going around, and I keep picking up these foam apples, and I'm like, ah! And I throw it away. And I pick up a good one, like, okay, I put that in my bucket, and foam apple, throw it away. The thing is that if it's at similar levels as the substrate, it'll slow me down. If the foam apples are at similar levels to, or even like at some comparable level, it could be 10 to 1, good apples to bad apples, or foam apples, they'll slow me down, yes.
Also, if you're throwing the apples away, that means that you're increasing the foam apples, or leaving the foam apples the same in the environment while decreasing the other.
Yeah, that's a good point. So if they're just popping off, I will relatively increase the amount of foam apples, yeah. But for argument's sake, let's just say there's an infinite number of apples, and we're just looking at it in the ratio. However, that being said, if like the foam apples are like 1 in a million, or imagine that I'm still waist-high to apples for whatever reason. This is a really weird apple orchard where I'm waist-high to apples and waiting to them. And only like 1 in every like football field's worth of waist-high apples is a foam apple. Basically, my rate's going to be the same. I'm going to be just dumping in apples, and I'll almost never encounter a foam apple. This is competitive inhibition. If I'm looking at these foam apples, it doesn't matter if I never see one. So here, raising the substrate concentration can overcome competitive inhibition. If all you are encountering are the real apples, the right substrate, and almost never encountering the inhibitor, then you're going at essentially the same rate that you would even if the inhibitor wasn't present. So what this means now is that Vmax is now unaffected. Ooh, I like circling things. This is like new functionality I just found. Whereas your Km will go up. Why does your Km go up? Again, let's think about our foam apples again for a second. If there's just apples, it looks like if I get to a certain space where, like, let's imagine there's 1 every foot. I go a foot, pick up an apple. Go a foot, pick up an apple. Right? I'm going relatively quickly, I'm doing okay. But the thing is if I introduce foam apples into that, now my rate is lower. Let's see, what is the next one I have here? Did I put in a slide that talks about this? Yeah. Yeah, I'll go back to the previous slide. So I'm going through and I'm picking up my apples and I'm throwing them in. But half of them are, let's actually illustrate here. As I have my apples, actually let's use apples. And pick in up, great. Okay. As I increase the number of apples, I'll do something like this, and I guess this would be the point. There's just so many apples I can't pick up anymore because this is my intrinsic rate. This is my Vmax. But if there are foam apples in there, let's imagine half of them are foam apples. Or, not say half of them, let's say that, actually a ratio is a bad way to do this. Let's imagine just for a moment that I'm in an area the size of this room, and 50 of the apples are foam apples. If I have 50 other apples, that means I'm going to be going slower, right? So let's imagine right here is 50 of real apples, and I have 50 fake apples. So I'm going to be going slower. let's imagine now there's 50 of the foam apples or 100 of the other apples, right? Well, then now it's like a 2-to-1 ratio. I'm going faster, but still not. So here's 100 of the real apples. We're fine. Let's say there's 150 of the real apples to 50 of the foam apples. Okay, I'm going faster, but still I can't go quite as fast as I would if they were all real apples. There gets to be a point, however, here. Let's say there is 30 million real apples in this room. It's basically filled to the brim with real apples, and there's only 50 foam apples. Basically, I'm never going to encounter those, so this is broken here. I'm basically back up to Vmax. So what we have here is something that goes like this. This is my inhibited rate, which means that if we look at half of Vmax here, since it lowered my rate at any given point, here's my Km. It's like 50 apples for uninhibited, whereas it's over here now for the inhibited. It's like more like 100. So it will affect Km, the half of the rate, that the half of the Vmax rate, but it will not affect the Vmax because you're going, if you get enough apples, it'll just overcome all the foam apples. Or if you get enough of the substrate, it'll overcome the inhibitor. There's another way to kind of look at this. It makes it, remember that Km is a measure of enzyme affinity. How easily or how quickly the enzyme will bind to the substrate. If you have an inhibitor in there, right, and half the time it's binding to the inhibitor instead of the substrate, it looks like it takes twice as long for the enzyme to bind to the substrate. Does that make sense? Because it has to bind to an inhibitor first, then it has to bind to a substrate. It makes it look like the enzyme has a lower affinity for the substrate. Does that make sense? Because it takes it longer to actually find one because you're finding the wrong thing more often. And so Km, again, being a measure of enzyme affinity, a competitive substrate will make it look like you have a lower affinity between the enzyme and the substrate. Okay. And this is just kind of demonstrating this. In a normal reaction, you have the substrate, it binds the active site, you have some sort of conformational change, it releases the products. During inhibition, however, what you have is something that looks like the substrate binds to the enzyme, and then nothing happens. And so it has to wait to be released before it can bind substrate. And it'll block substrate until that time. Remember our Lineweaver-Burke plot? What's plotted along the x-axis? 1 over the substrate concentration. What's on the y-axis? 1 over, say it louder. Still really quiet. 1 over v. Yep. So you have 1 over v. What does our y-intercept mean? This is really important. This will show up on a quiz and or a test and probably both. 1 over v max. Yes. So right here is 1 over v max. Right there. What is the x-intercept? Yes, negative 1 over Km. Okay, so with competitive inhibition, you know which ones these things change. What will competitive inhibition change? What's that? It changes Km. What doesn't it change? Vmax. So how would an inhibited line look different on a Lineweaver-Burke plot than a uninhibited?
It has a different slope, but the same intercept.
Which intercept?
The y-axis intercept.
Yeah, exactly. So you have a different slope. The y-axis intercept should stay the same because your Vmax stays the same. So your 1 over Vmax is going to stay the same. So that is going to stay basically the same. However, your slope is going to change. So that is going to change right here. Actually, I can do like the pointy thing. Right, okay, so 1 over Vmax right here will not change because we're keeping Vmax the same. But down here, the negative 1 over Km will change because our Km is changing. Our apparent affinity between the enzyme and the substrate is changing. Okay, let's talk about another one, non-competitive inhibition. Now, if you're in biochem, this terminology is going to be slightly different. I am going based off these terms, depending on if you're on the biological side or the chemical side, tend to sometimes get used differently. And I am taking the approach that your book takes in how to refer to these. And just know that this terminology can be slightly different depending on the field that you're talking about. Non-competitive inhibition here. This is an inhibitor that's going to bind to a different location than the active site. So it's not competing with the active site. And this is going to cause a conformational change in the enzyme. So it's going to change that, including it's going to change the active site. Now it doesn't interfere with the substrate binding, but it does interfere with the proceeding of changing the substrate. Therefore, your Vmax is going to decrease, but your Km remains unaffected. Okay, I'm picking up apples again, right? And I don't have foam apples this time, but I have this really affinity for shiny objects, and I get distracted. This is actually pretty close to the truth. I really get distracted. I'm going along, and I'm picking up apples. And I can still pick up apples at the same rate, but then all of a sudden I find something shiny, I pick it up. And then once I pick up that, I'll pick up another apple, but then I don't know what to do with it. Because it's shiny objects. Cool. It's a fake one, by the way. I'm not just looking at my hand. I guess I could look really weird. And so I failed to put the apple into the bucket. Now, I can pick up apples at the same rate, right? It's not going to change my affinity for the apples. I can still go out and grab them just as fast because my other hand, my apple picking hand is still free. But my ability to then dump it in the bucket gets inhibited. So what happens here is that the affinity for the enzyme to bind to the substrate is totally unaffected. You're fine. You can still bind to it. But to actually change it once you do slows down. So essentially I can pick up those apples just fine. I'm going to put in the bucket and get the next one kind of slows down. So I can't go, my total rate isn't as fast because I'm just trying to, with the shiny thing. So this is kind of how we look at this. You have an inhibitor plus you have a substrate. You have two binding sites here. You can either bind the inhibitor or you can bind the substrate. If you just bind the substrate, hey, everything's great, and you can just proceed here. So if you just bind the substrate here, everything's great, and you can just proceed down this way, go through catalysis, and that's great. Perfect, no problem. Just the way it's supposed to. However, if you come down this way, and you bind the inhibitor first, a couple things can happen. You can also bind the substrate, and nothing happens. If you have the inhibitor plus the substrate both bound, nothing's going to happen. However, this could pop off. So that inhibitor could also pop off. You could then bind the substrate, everything's good. You could have both of them bound for a while, and then the substrate or the inhibitor pops off, then you go and everything's good. But the point is that this doesn't prevent you from binding the substrate. You can bind it, it's fine. If you also have the inhibitor bound, nothing will happen. And so, what would this look like? Again, this is our Lineweaver-Burke. What would the Lineweaver-Burke plot look like compared to a normal enzyme if it has a non-competitive inhibitor? What's that? Yes. X-intercept remains the same. So down here, because our Km is unaffected, but because our Vmax is, we're going to have a different Y-intercept. So essentially, same x-intercept, different slope. Because our affinity is the same, but our Vmax is affected. Are there any questions with inhibition? This is a common way to control rates of enzymes sometimes. If we want to slow them down, we can inhibit them somehow. Yeah.
So with the non-competitive inhibition, is other times, so does it always happen where it's complete inhibition, or are there times the inhibitor just slows down the catalytic reaction?
In truth, there are times where it just slows it down instead of complete inhibition. Now that being said, that's kind of beyond the scope of what we're going to talk about here. But yeah, for the most part, what we'll talk about in the future will be complete inhibition when that happens. But there are times where you actually have modulation happening. And sometimes, in fact, this actually kind of opens up into an entire, and we're going to talk a little bit more about this, entire other field where actually you can have things bind to the, instead of having an inhibitor, so to speak, you actually have like essentially a missing part of the enzyme that binds to another site and activates it. So you can have essentially the same thing happening, but activation happening as well. So it needs that to go. And we'll talk more about that in a minute, but that's a good question. Yeah, cool.
Is inhibition how painkillers work?
Some of them, yes. Actually, and it's kind of inhibition in that what you have is not so much an enzyme that's working, but generally you have a channel that is allowing, and often this is in nerves, you have channels that allow ions to go across a membrane, and this causes a neurologic impulse, like for instance sodium potassium. What you can do is combine things to those channels that will decrease the amount of ions that can go through and can stop that nerve from conducting impulses. And so that's how some of them work. Now that being said, actually there's a ton of different mechanisms of painkillers. They don't just do that. Sometimes they inhibit synaptic junctions. Sometimes they can actually break down a neurotransmitter between synaptic junctions. There's a lot of different ways of that. If you're really interested in that, we go into more about kind of how the actual molecular biology of how the nervous system works and how that can be interrupted by drugs and allergies. Not something we get a ton into here, but yeah, that's a good question though. Some of them, yes. Anything else? Okay. So with that, we've been talking about enzyme activity. Let's talk about a little bit about metabolic control now of enzymes and how can we modulate the functioning of enzymes once we actually have them up and going. They're not inhibited necessarily, but we want to affect their rates. One of the primary ways that enzyme activity is controlled is through pH. So remember your throat. Okay, I gotta really stop walking around if I'm going to be that clumsy. Or have different shoes on. Okay, so pH, remember that, okay, so enzymes fold, they get their tertiary structure between interactions between the different side chains of the amino acids, or the amino acid residues. And you also have interactions with the environment. Remember that pH, essentially we're adding or having less of these positively charged protons, these positively charged hydrogen ions. And it's really these electrostatic charges that are in a large degree changing or causing the folding of this protein. If you have more or less of these charges in the environment, that will change how the protein folds, or the structure of that protein. Okay? And so what that means then is a protein is only going to be able to function within a certain range of pH, only within a certain range of the presence of these protons swimming around in solution. Does that make sense? If you have too many or too few, the interactions between your amino acid side chains in the environment and also with each other, because we could protonate some of those side chains and cause them to act differently, is going to be different. And so once we get outside that range, just the conformation of this protein is not going to work anymore. The active site might be changed, the actual charges in the active site might be changed. The ability of that protein to change its conformation once something is bound to it might change. And so in a certain range of pH, everything works great, but you go outside of that, it breaks down. So every enzyme has an optimal range of pH. So just kind of, for instance, what you would see is if you look at the maximal activity or the Vmax of an enzyme within a range of pH, one is going to have something like this. So like we'd have, okay, it works somewhat between 4.5 and 7.3, imagine. It has an optimal activity just below 6, activity here just below 6, but its range, it drops off. If you go away from 6, either higher than 6 or lower than 6, it drops off really quickly, and there's a certain range outside of it, it just stops working altogether. Perhaps you have some other enzymes that work really well around between 1 and 4, and it has a maximum range around a little over 2.3. A lot of enzymes in your stomach are like this. Enzymes that you have to break down, like proteins. There's trypsin and chymotrypsin and a few other different proteins in your stomach that are ideal for breaking down proteins as it reaches your stomach. They only work at these really low pHs. And then we have some others, for instance, that only work at really high pHs. Actually, these aren't so high pHs, this is kind of normal. It's actually still kind of low for what you find in your body. But the point is that enzymes have this optimal pH, and you can modulate the rate of their functioning by altering the pH. If the pH changes, the ability or the maximum rate at which an enzyme operates will also change. So anytime that we talk about the rate of enzyme activity, that is dependent on the pH that you're looking at. So the specific ways this can happen, for instance, you have protons bind to the enzyme at low pH. This can change the charges on amino acid side chains, so they don't interact the same way anymore, especially if they're in the active site. At very high pHs, where you don't have many protons in the environment, protons can be released from certain side chains, again changing the charge and causing them to interact in the way that you would expect them to otherwise. And all of these things are going to be able to change the conformation of the protein, but also you can change the charges in the active site and change the way that the active site interacts with its substrate. And actually, this is one, again, I'll just come back. This is really commonly used, again, like for instance, you have all these enzymes. This is like an example while you're writing this down. In your stomach, you have all of these enzymes that only work at really low pHs, which is really good because a lot of the enzymes in your stomach are insanely destructive to organic molecules. Like, they are made to break down living or once living tissue. Now, in the cells that they're made in, aren't at that pH. They're around a low pH. They're like kind of a normal pH. They're like around 7.5 or something like that. So you make these enzymes, they're not working inside the cells they're made. This is good because if they were working, they would like totally kill the cell. They'd start breaking everything down and just, that would be bad. Like if your stomach started to eat itself because it was making these enzymes that break itself down, not good. However, once they get released into the stomach, the pH changes. They become active because of the different pH, and then they can start going to work. So oftentimes we can use this to only make enzymes work in the places that we want them to work and not work in other places that we don't want them to work. Does that make sense? It's kind of a cool system. Another way that we can change them is through covalent modification. Something needs to be bound to the enzyme for it to work. Now remember again that this is one of the things that we were talking about. For instance, coenzymes. One of the ways that this often happens is by addition or removal of a phosphate group from a protein. You can phosphorylate it, you can dephosphorylate it, and one of those will either inactivate it, activate it, turn up its activity, turn down its activity, but we can change its activity by adding a phosphate group. This is happening through the process we call phosphorylation, dephosphorylation, big words. I'm probably in the wrong profession if big words just don't agree with me, but okay. Phosphorylation, just adding on a phosphate group, dephosphorylation, popping one off. This happens through a classes of enzymes that are they're called kinases that add phosphate group or phosphatases that chop them off. We're actually going to talk about this quite a bit. There's quite a few enzymes, particularly in metabolic functions, that need to get phosphorylated before they work. or they need to be dephosphorylated before they work. And so this is actually a really common one. The reason, I think one of the reasons why this is really common is that, hey, we have tons of ATP around. And we have lots of other enzymes that are good at phosphorylating or dephosphorylating things, so it's a really good system to change how things work. Also, one other thing that we have is enzyme-enzyme interactions. Enzymes that have to interact together, or enzymes that have to be in certain places in the cell to work. So for instance, what you can do is you can arrange enzymes using the cytoskeleton or other organelles to place them where you want them in the cell. So for instance, we can make essentially an assembly line. And we're going to talk about this a little bit later on as we're talking about some metabolic processes. If we need substrate to be passed from one enzyme to another, to another, to another, what we can actually do is have enzyme 1, call it E1, and actually anchor it onto a cytoskeleton. And then it takes substrate, so substrate 1, and makes that into product 1. Another enzyme then, let's call this E2, needs to take product 1 and make that into product 2. Let's imagine we have another enzyme here, say enzyme 3, okay, making E's apparently also is outside my skill set. Enzyme 3, and that makes that into product 3, and this is what we want in the end. So we come from the substrate, and we pass it along these 3 enzymes to eventually get the thing that we want. This is actually a really common thing. We do this a lot in different syntheses. We do this in metabolic processes where there are multi-step reactions. And one thing that you can do is we can anchor all these to the cytoskeleton and keep them in close proximity. If they're just free-floating like out around the cytosol, and the cell is a really big place compared to an individual enzyme. I mean, we're essentially talking like you wandering around in the state of Washington. I mean, really, really big differences between the size of an enzyme and the size of the entire cell. It really will not work all that great if you're just wandering around hoping you run into the thing that you need. Like, for instance, it works a lot better if we keep you close to your food, like into the calf, or keep your food close to you, rather than just saying, hey, here's the county of Walla Walla, go find some food. It doesn't work so well. It works more slowly. If we want quickly, we should have you close to it. I don't know, that analogy just it didn't work so well. But the point is being, if we need this to happen, if just product 1 is just floating through the cytosol, and so is enzyme 2, and they need to find each other, that's going to be a much slower process than if enzyme 2 is anchored really close to enzyme 1, and product 1 is just right there when you need it. And so what happens then is we get oftentimes multi-enzyme complexes. So you can actually have enzymes attached to each other physically. We have enzymes attached to the cytoskeleton. And this allows you to have more control over the rate. Actually have the rate go significantly faster than just normal simple diffusion throughout the entire cell and hoping things crash into each other. Another form of control that we have over enzymatic activity is this thing called allosteric regulation. So, like we were talking about with non-competitive inhibition, an enzyme often has more than one binding site, more than one place that can bind a thing. The site that's not the active site that can bind something is known as the allosteric site. Molecules that modify an enzyme allosterically can be either inhibitors or they can be activators. They can be either one. So, like we were talking about before, we can have inhibitors that decrease the function, completely turn off the function. But we can also have other things that bind that increase the function, or essentially turn on the enzyme and remain completely off. So what we were talking about earlier can go in both directions. So it'd be something kind of like this. we have a certain reaction, and this is kind of showing you almost exactly what was happening with allosteric or non-competitive inhibition. On the top up here, the entire thing just proceeds normally. You have the substrate binds to the enzyme, makes the enzyme substrate complex, and then it releases the products. Whereas if we have, say, an inhibitor, or this could be the other thing, it could be an activator. You could have here an active site that's not the right shape or the right conformation. Before this gets added, once it gets added, it then can all of a sudden bind to the substrate. Another way that we can control the rate of reactions is to couple those reactions with ATP. This is particularly important when we have reactions that normally have a positive delta G. What does it mean if you have a positive delta G? Can anyone remind me? What's that? Yeah, it's going to require some external input of energy. That's because the reaction just by itself actually has a decrease in entropy from the beginning to the end. The reactants have a higher free energy, or the products have a higher free energy than the reactants did. So we have to come up with that free energy somewhere. And what we do is we use ATP. Now ATP, just kind of as a reminder, is an adenine plus a ribose. So here's our adenine, here's our ribose, our 5-sugar, and then we have phosphates, we have 3 of them. So up until here, this is exactly what we were seeing in RNA that we were talking about before, but we're going to stick on these extra 3 phosphate groups. And these are nice high energy bonds that we can donate to reactions. By breaking these bonds, that has a really nice large negative delta G that we can essentially steal some of that release of free energy to help power something else. So for instance, just right here, the hydrolysis of ATP to ADP plus a phosphate, that has a delta G, standard delta G of negative 7.3 kilocalories per mole. Does anyone remember what the standard free energy meant? Say it a little louder. Oh, I thought you said it. No. Okay. This is the delta G that you get under standardized conditions, which is not necessarily physiological conditions. Under physiological conditions, it's actually more like 11.3 kilocalories per mole, a drop at 11.3. And that's not always exactly the same. It depends on the type of cell, it depends on where it is. That's kind of approximate. Again, that will change depending on the environment. Okay, so let's look at something here and demonstrate how it's done. Imagine we have some conversion we want to make, something from A to B. We're going to have this chemical change here, and this has a change in free energy of positive 3 kilocalories per mole. So we actually have an increase in free energy, and that's not favored. That's not going to happen spontaneously. And an enzyme can't help you there because, just by itself, because an enzyme is not going to change the equilibrium of each reaction. It cannot make a reaction proceed that would not otherwise proceed. We can always change the rate. However, if we can couple this to a hydrolysis of ATP, where again here we have this drop of 11.3 kilocalories per mole, and actually steal some of this to pay for this, what we can end up with is still, for the entire reaction, the entire system of reactions, a drop in 8.3 kilocalories per mole. So this is still a pretty good ability. This is still a reaction now that will proceed at a pretty decent rate if we use the coupling of ATP plus ADP, or hydrolysis with ATP to ADP. So ATP, for this reason, is constantly being produced and consumed. There is a pretty high flux of this happening all the time inside you. If you look at the cellular concentration of ATP at any given time, in ammonia it's about 1 to 10 millimolar. Which is actually pretty high for concentrations. Oftentimes, for a lot of constituents, other than like major organic molecules, we're talking about micromolar instead of millimolar, but this is pretty good. Now, the total content in you, then, for the size that you are, you have about 1/10 of a mole of ATP in you at any given time. That's not a whole lot. However, does anyone want to guess how much ATP you use in a day?
5%.
What's that?
5%.
5 or 10 moles. Yeah, a little bit more than that. That's a good guess, but somewhere between 100 and 150 moles of ATP. A lot. This actually comes out to somewhere between 50 and 75 kilograms of ATP. For some of you, that's how much you weigh. Probably a little bit less than you weigh, actually. I weigh a little bit more than 75 kilograms. So what this means then is that you have to recycle ATP really often and quite a bit. Each individual molecule of ATP is turned to ADP and back into ATP about 1,000 to 1,500 times per day. That process of making ATP, taking ADP and turning to ATP again, is absolutely vital for essentially every living thing on Earth. If you shut that down, your biology can last hardly any time at all. And really metabolically active tissues, like your brain, your nervous tissue, needs like insane amounts of that. So that's really important. Okay, that's all I have for you today. We're going to go into talking about the cell membrane on Wednesday. We're done with enzymes. Oh, not Wednesday, Friday, because it's what's that? Service day. Oh, service day. I think you said Thursday. It's not Thursday. It's Thursday. Make sure you sign up for something on that. You will have a quiz on Friday, a great quiz when you come in to let you know. And then also remember there's a test next week on Wednesday. Just want to make sure you're thinking about that. My plan is yes, that. Hold on, I'm good.